Welcome, everyone, to another episode of our series podcast, Finals in a Pod, brought to you by Study Sheep and the Addendum Club. Today, our guest is Professor Jason Lee, who's going to help us with organic chemistry. Thank you for recording with us, and let's jump right into the questions. So our first question for you is, what are D and T, and how do they affect reactions?
Okay, D and T, maybe that person meant D and L.
That's possible. I don't know.
So D and L are labels that we put based on how a compound rotates in plane polarized light. D means dextro rotatory, and L means levo rotatory. It just tells you which way the compound is rotating when you shine it through the plane polarized light. In terms of what products are formed, it's not really too relevant. Whether something's R or S is much more relevant to the course. D and L is sort of older notation now that people don't tend to use very much.
Okay, next question is, what's the difference between an alkane and an alkyl?
Okay, alkane and alkyl. Okay, so when you have a molecule which is just carbon single bonds and carbon-hydrogen single bonds, we call this an alkane. So that's by itself. Now, when it is part of a much more complicated group, like, for example, there's an alkene, there's an alcohol, there's other groups within the molecule, then that portion of the molecule could be called an alkyl. So alkane is the thing itself. Alkyl is when it's a smaller part of a larger molecule.
Okay, thank you for that. And what's the difference between isomers and constitutional isomers?
Okay, isomers is a general name that we have for anything that has the same molecular formula, but that are different. Okay, so that's an isomer. A constitutional isomer forms part of the isomer subclass, but it's instead differentiated by specifically the way the bonds are connected. So that's the difference. So a constitutional isomer is a subclass of isomer, and it's a specific isomer where the bonding is different.
How does resonance correlate with molecule stability?
Anytime a molecule has resonance as a whole, so we're talking about something negative or positively charged overall. If it has resonance, it is going to be stabilized. The more resonance structures it has, the more stabilized it is.
Okay, thank you. What's the inductive effect, and how do we use it while determining acidity?
The inductive effect is what I like to refer to as long-range electronegativity effects. So it applies in acids and bases when you're trying to determine which is a better acid. So how it works is if you have an electronegative atom, such as fluorine or bromine or chlorine, bonded far away from the acidic hydrogen, it's going to have a long-range effect. It's going to pull electron density away from the area that has the acidic hydrogen. This causes the substance to be more acidic. The more electronegative the atom is, greater the inductive effect, and the closer the electronegative atom is to the acidic hydrogen, the greater the effect.
Which is the most stable, a terminal alkyne or an internal alkyne?
Technically speaking, it would be an internal one, but I don't see the relevance. I can't think of a reaction where it would matter which alkyne is more stable.
What do we do with a branched branch when naming cycloalkanes?
Okay, this is a branch. So maybe that particular branch can be given a special name like sec-butyl or tert-butyl or isobutyl. But if it's a branch of a branch is very complicated, we don't actually cover this in this course. You would find if you look up nomenclature rules in IUPAC, you would see that you have to use parentheses, but we don't actually cover this in the course.
Okay, thank you for that. When you have a functional group and an alkene or alkyne, which one takes priority for the lowest number?
So an alkene and an alkyne, which one takes priority for the lowest locant or number? It's the alkene. The alkene is considered to have higher priority over the alkyne. Now, I know why this question was asked. I think I know why. Is because when we name the functional groups, we call it an ene-ine instead of an ine-ene. And normally, the thing named last is the one that has higher priority. This is somewhat of an exception. We call it an ene-ine because that's what the IUPAC decided. But in terms of priority, which is what you need to use to determine which order to label the locants, the alkene is more important than the alkyne.
Thank you. What's so special about benzene?
What's special about benzene is its resonance. It's a neutral molecule that just happens to also have resonance structures. So that gives it a great deal of stability. So that's why they don't do the typical reactions that we expect out of alkene. It's too stable. It won't break unless you have specific conditions, conditions which very often include or require a Lewis acid.
How do you use ortho, meta, and para when naming the dibranched benzenes?
If the groups are in a 1-2 position, we refer to this as ortho. If it's 1-3, we refer to this as meta. And if it's 1-4, we refer to this as para. How we use it is we need to add it to the names of the molecules that have those exact positions in the front of the molecule. So either by writing para completely or by writing a small p, followed by a dash, and then the rest of the molecule.
What's the difference between benzyl and phenyl in common naming?
Phenyl is a benzene ring substituent, whereas benzyl is a toluene substituent. So what I mean is that if you have a benzene ring C6H5 substituent, this is what we call a phenyl. And if it's C6H5CH2, that is a benzyl substituent.
How does branching affect constitutional isomers' boiling point?
This is a very good question, but boiling point is not part of the course this term. So, I mean, I can give the answer. Essentially, branching is not good in general for boiling point if you're comparing two alkanes of the same number of carbons. So, branching lowers the surface area and the ability of alkanes to stack on top of one another. So this decreases the boiling point. But again, if you're listening to this podcast, it's not part of this year's final exam.
What's staggered and eclipsed conformation, and what's their difference?
Okay, so all alkanes in general have something called free rotation. In other words, you can rotate the bond freely around a specific atom or bond. If you rotate it in such a way that all the positions are on top of one another. So in other words, if you're looking straight down, the ones in the back are being hidden by the ones in the front. We call this an eclipsed conformation. So it makes sense, I think. Staggered is when they are not on top of one another, but when they are separated fully and you have perfect spacing between all the groups from the front atom to the back atom. So that's staggered. And in general, staggered is going to be more stable than eclipse.
Okay, thank you. And what's the difference between torsional and steric hindrance?
Torsional strain is what we refer to small groups or atoms, specifically mainly hydrogen. So when you have two hydrogens in very close proximity or in a staggered formation, we can say that there's torsional strain. Steric hindrance is the more important and larger undesirable effect. So whenever you have something much larger than just a simple hydrogen, for example, a CH3 of another CH3, or even something bigger, this is what we refer to as steric hindrance. So they are both things that are related to proximity, but Torsional strain is small, like an atom like hydrogen, where steric hindrance is more important. It's a bigger group, like a methyl group.
Which cycloalkane is the most stable and why?
The most stable cyclohexane is definitely cyclohexane, or the six-membered ring. The reason is because there's less ring strain. So in other words, in its 3D form, the chair, the bond angle is perfectly 109.5. In other cycloalkanes, for example, cyclobutane, the bond angle is less than the ideal 109.5 of an sp3 carbon. So because of that ring strain, the ring is slightly less stable. Now it still exists, but it is less stable.
Is a large branch more stable in equatorial or axial position?
The equatorial position is going to be, in general, most stable.
What's the difference between diastereomers and enantiomers?
Okay, so diastereomers and enantiomers are both stereoisomers, which is a class of isomers, which differ because of their 3D. Enantiomers is defined as non-superposable mirror images. And diastereomers is defined as non-superposable, but they are not mirror images. So how I like to think about it is this. Okay, so remember the definition for enantiomers, which is non-superposable mirror images, and anything that doesn't fall into this category is a diastereomer. So a diastereomer is the everything else category. There are three main types in this course: cis-trans in double bonds, cis-trans in rings with at least two groups, and when you have multiple chiral centers where only one or where not all of the chiral center changes. So for example, if you have two chiral centers and the original molecules are R and the second molecules are S, this is an example of a diastereomer.
How do you tell if a compound is chiral or not?
The requirement for a chiral carbon, since we're focusing on organic chemistry here, is that it has to be an sp3 carbon and it has to have four different groups attached to it. So if you have a molecule with only one chiral carbon that has that requirement, four different groups attached to it, then the molecule is chiral. If you have more than one chiral center, the molecule is usually chiral, except if it's a meso, which is a very specific case that you see.
How do you determine priorities when determining stereochemistry?
How do you determine priorities when determining stereochemistry? I don't see the relevance between the two things. Priorities is determined by looking at the atomic number of the atom directly connected to the chiral center. And if there's a tie, you try to break the tie by going further along the branch. Stereochemistry is just a general term for anything 3D relating to a reaction.
What do you do if the lowest priority group isn't pointing away and you have poor 3D skills?
Okay, if the group is pointing towards you, what you can do is you can read directly and invert. So that's if the fourth priority is pointing towards you, you just read directly and invert. Now, if the fourth priority is pointing to the side, what you can do is you can swap it with the group that's in the back. You read the priority after the swap, and whatever you find, whether it's R or S, you invert that answer to get your original RS. The idea of that for doing that is by doing a swap, you've created the enantiomer. So when you read it, well, you can read it now since the fourth part is in the back. You have read the RS of the enantiomer. To get the original molecule back, you just have to flip it. So again, you swap the fourth priority to the back with whatever group is in the back, read RS directly for that molecule, and then flip it to get the original molecule.
What's the difference between E and Z compounds?
E and Z, so this refers to alkene labeling. If an alkene has the first priority for both carbons of the alkene on the same side, we call this alkene an Z alkene. And if, on the other hand, the first priority on either carbons are on opposite sides, this is what we call an E alkene.
Yeah, what is a meso compound?
So meso compound is a compound that, number one, has at least 2 chiral centers. So the meso compound is a specific compound which is symmetric. It has a plane of symmetry, which may or may not be visible, but it is a symmetric compound that does not rotate plane polarized light. As a result, we can call it an achiral compound, but again, it must have at least 2 or more chiral centers.
What is a racemic mixture?
A racemic mixture is a 50-50 mixture of two enantiomers, so R, S, for example.
What is a nucleophilic substitution?
That is one of the 20 reactions that you need to know for the final exam. A nucleophilic substitution is when a nucleophile attacks an alkyl halide to form a compound that varies depending on the nucleophile.
What is a beta elimination?
This is another reaction that you need to know for the final. A beta elimination is when you have a base and a beta hydrogen within an alkyl halide, and the base attacks the beta hydrogen, forms a double bond, and the halogen leaves to give you an alkene.
What is the difference between a Zaitsev product and a Hofmann product, and how do you know which one it is?
So the Zaitsev product is what we refer to as the stabler alkene product in a beta hydrogen elimination, whereas the Hofmann product is the least stable alkene in that same elimination reaction. How you determine which alkene is more stable is based on the number of non-hydrogen groups attached to the alkene. So an alkene can have a maximum of 4 non-hydrogen groups attached to it. So the Zaitsev product will have the most number of these non-hydrogen groups, or R groups, attached to them. And the Hofmann product will be along the side where there's the least number of R groups, or non-hydrogen groups.
What factors affect whether reaction will occur between a base and a haloalkane?
I'm going to assume here you're referring to beta elimination. So beta elimination will occur if the base is strong enough. So you're thinking maybe OH minus, something like OH minus or stronger is typically good enough to do an elimination. Remember that a base can also act as a nucleophile. So it's possible that instead of doing this elimination, it might instead do a substitution. So you have to keep an eye on the other factors as well. For example, is the alkyl halide primary, secondary, or tertiary, which tends to be more important than what the base or nucleophile is.
What is a bulky strong base, and how does it affect reactions?
The bulky strong base that's used a lot in this course is potassium tert butoxide, or what I like to call KOTBU. It has a very bulky tail, so as a result, there's 2 main things that it does in the course. Number one, it doesn't really do substitution reactions. So even in a case where you have a primary halide where substitution is favored, KOTBU will instead form the elimination product. The second very important case when we use KOTBU is when you have an elimination that you need to do and you want the Hofmann product. So whenever you want the Hofmann product, you use KOTBU. So you need a bulky base to favor the Hofmann product. If you use a small base instead, like NaOET or NaOH, you will form the Zaitsev product.
How do you perform a synthesis reaction?
Well, you go to a lab and you add the chemicals together. But I don't think that was the intention. So maybe the question is, how do you solve a synthesis problem? Unfortunately, this is not something I can just say in a podcast. So you'd have to go by the many, many examples that your teacher showed you in their class. I would say the key thing that you need to solve synthesis problems is very good knowledge of all 20 or so reactions in the course system. If you know all the reactions in the course, what the starting material is, what's on top of the arrow, and what the product is, if you know this really well, all 20 of them, you should pick up hints based on the starting material or the product of the synthesis that guides you what happened. So the more you know your reactions, the better you will be able to decide or to know how to do a synthesis.
What is Markovnikovs rule?
Markovnikovs rule is a rule that is used in general for a reaction where you have an addition of a smaller molecule. It states that the hydrogen will add to the carbon with the most hydrogen. What that usually means is that the other group, for example, a Br minus, will add to the other carbon. So that is Markovnikovs rule, and we apply it for two main reactions, the addition of HX and the addition of H2O in the presence of H+. So these go Markovnikov.
Why does a skeletal rearrangement happen in carbocations?
So a carbocation is a group that has a plus charge on a carbon. So no one really knows why it happens. All we know that it does happen, and the reason that we speculate why it happens is because a rearrangement usually causes a carbocation to be more stable. So, for example, you may be going from a secondary carbocation to a tertiary carbocation. So this is more stable. So the molecule recognizes this, presumably, and decides to rearrange. Likewise, maybe you have ring expansions for the same reason, because you're expanding the ring, you're lessening ring strain, so it wants to do it because it gains stability. So we don't know exactly why, but we suspect it has to do with stability, at least based on the examples that we see.
What is ozonolysis?
Ozoneolysis is one of the reactions that you need to know. For the exam, it is a reaction where you add ozone with another molecule such as SME2. What that does is it causes a double bond to break or split apart, and you insert oxygens on either sides of the broken double bond.
What is useful about retrosynthesis?
Retrosynthesis is a typical strategy that you use to maybe simplify synthesis problems. I personally don't put too much emphasis on it, but it's essentially you solve a synthesis by going backwards. So in other words, you see what the product is, and you try to go backwards to get back to the original starting material. I think there's some use to it, but you should also look at the starting material. Sometimes the starting material gives you clues directly on what you need to do for synthesis. So look at both the product and the starting material. And since our syntheses are not that long, usually typically around 3 steps or so, I don't think you need a full retrosynthesis analysis, but again, it depends on what your teacher taught you.
What are the 3 conditions for aromaticity?
Okay, so these are what we call Huckel's rules. So there are 3 of them. Number 1, the ring must be planar. This is generally the case, except if you have something specific like a 10 annuline ring. Number 2, each atom in the ring must have a p orbital or free p orbital. And number 3, it has to obey what we call, this specific one is also called Huckel's rule. It says that it must have 4n plus 2 electrons within the ring, where n is an integer starting from 0. So in other words, the ring must have either 2, 6, 10, 14, 18, etc. electrons inside the ring for it to be aromatic. So you need all three for the molecule or the ring to be considered to be aromatic.
What is activating and deactivating branches?
So this refers to benzene rings. So if you have a group which is activating, it's a group that is donating electron density in some way. Whereas if you have something which is deactivating, it is withdrawing electron density away from the ring. Activating groups typically have either a lone pair directly on the atom bonded to the benzene ring or are alkyl groups. With one exception, halogens have lone pairs, but they are considered to be deactivating groups due to their electronegativity. In addition to halogens being deactivating groups, any species which are either positively charged, like a nitro group, on the atom directly attached to the ring, or the atom directly attached to the ring has a slight positive charge due to close proximity to many electronegative atoms. For example, SO3H, the sulfur is delta plus because it is surrounded by multiple oxygen.
Okay, so we've reached the end of our questions. Thank you so much for your participation, Professor. We hope this podcast helped you, dear listeners, and good luck on your finals and have a great summer.